Hello everyone. I will present our work about the language-independent speaker anonymization approach using SSL models. To begin with, I will give the introduction about the speaker anonymization system and our motivation. Next is the details of our systems, followed by the experiment results and analysis in English datasets and also Mandarin datasets. The conclusions and future work will be given in the final part. Thanks to the VPC challenge, they give the definition of the speaker anonymization. The task is to suppress the speaker's identity, meanwhile preserve the linguistic content and other paralinguistic attributes, which allows downstream tasks. They also provide common datasets and baseline evaluation metrics. We basically followed the protocol of them, and we take the one more powerful baseline called B1. It's ASR and TS-based models. During the inference stage, how we can see how they can anonymize the speech. So there are actually 3 steps. Firstly, is to disentangle speech into F0, linguistic features, and also X vector. They assume X vector contains encodes speaker privacy information. So by anonymizing X vector using some anonymization method, and the speaker privacy can be protected. The final part is to synthesize anonymize the speech using source or original F0 linguistic features and anonymize the X vector. Actually, these systems has been proved is effective to the English anonymization. But we were wondering whether we can create one SAS that can anonymize speech from unseen languages, not only English data, but also Mandarin or Japanese or any other languages. Actually, if we directly use B1 to anonymize the Mandarin data, the content of Mandarin is distorted. Because of the language-specific ASR acoustic model in the B1. So actually this is a language-dependent model. So we propose to replace this language-dependent ASR AM model with language-independent SSL models. These models train in a self-supervised way and can provide general context representations. The second contribution is we update the TDNN to the state-of-the-art eCover TDNN. As we know, speaker identity is very important to speaker anonymization. So this is investigation of the speaker encoder. The third part is we to make the system more efficiently. We use hi-fi GAN as a speech generator rather than the traditional TTS pipeline. Next, I will give the details of each of part of our proposed systems. The first part is SL-based content encoder. We mainly focus on the Hilbert-based models. As we know, there are 2 common ways to use Hilbert models. The one way is to use continuous features extracted from the hidden layers, which contain both context and speaker information. It's obvious that not suitable for speech disentanglement. the speaker information would be dictated from the context features if we directly use these continuous features. Another way is we use Hilbert k-means model, apply k-means over the Hilbert continuous features to obtain the discrete features that is helpful to get rid of the speaker identity attributes from the context features. But unfortunately, inaccurate discrete features would lead to incorrect pronunciations that would cause the poor WER. We propose to use Hilbert-based soft content encoder, which aims to comprise a better trade-off between continuous and discrete features. This is a outline. This is the structures of the soft content encoder. The blue blocks, the parameters of them would be updated during the training stage. And we replace the last of layers of Hilbert models with linear projections to extract soft predictions and try to predict the discriminated distributions of these soft predictions over the discrete targets extracted from the Hilbert k-means. Hopefully, it can achieve a better trade-off between these two features. The next part is a speaker encoder. Besides the standard configuration, which uses F-bank as the input features, we also implemented SE-kappa, which uses SSL as the input features. Particularly, actually, this is a weighted average from all the hidden layers of the pre-trained Hilbert models. After getting the speaker features from the pre-trained E-kappa TDNN, also the context features from the pre-trained Hilbert-based soft encoder, and plus the F0, we can pass them to the hi-fi GAN to generate the audios. Okay, let's move on to the experiment. We follow the voice privacy evaluation plan and do the experiments in English and Mandarin data. There are two main evaluation metrics. One is EER, indicates privacy. Another one is WER, indicates utility. That is how the speech content preserved. For the EER part, there is actually this is a game between users and attackers. Also, according to the knowledge attackers have, there are two types of attackers. Let's see. One is a very weak attacker because they are unaware of users anonymized speech that users provided, so they directly use the original speech. Another one is a little bit stronger attacker because they try to use similar SAS to get the anonymized speech, anonymized speech, even though they don't know the specific parameters. So, this kind of attackers would get the different pseudo speakers with the users. And for the WER, we test with anonymized speech. So if this WER is close to the original speech, that is perfect because the speech content is preserved. And also we notice the ASV Evo model and also ASR Evo model. It is noted that it is a language matched models. It's trained on English data. If we test on English data, to get more reliable EER and WER results. Here are the datasets information for the English experiments. This is a speaker anonymization, English speaker anonymization results. So first, let's look at the ER results of one of the datasets, test sets. Yeah, there's 3 different systems. One is a baseline. Another 2 is our proposed Hilbert-based models. One is using SE kappa, another one is use FE kappa. It's clear that our systems achieves comparable ER with the baseline. And also for the WER, and we can say our systems achieves better WER, lower WER, which is good to protect the speech content. In summary, from the English speaker anonymization results, we can say that our proposed SAS can protect the speaker information almost as well as the baseline one. Also provides more reliable linguistic information. Here are the results about Mandarin speaker anonymization. We created the test set, Mandarin test set sampled from AISHELL-3. And for the 2 evaluation models, both of them were trained on the Mandarin datasets. If we look at these figures, firstly, for the OA conditions, our proposed systems can achieve about 40% ER and also 23% ER on the AA conditions. This values means the proposed method can be adopted to other languages like Mandarin successfully without any language-specific models or sources, and it's simpler than the baseline as well. But if we look at the CER, actually it will increase it to about 20%, but the original one is about 10%. So there is a degradation on the speech content. Now we can answer the questions we left at the beginning. Yes, we can use our proposed SAS without any language specific resources models to anonymize speech from unseen languages. But there is still room to improve the performance of these systems. Actually, our next paper also analyzes the performance bottleneck of these systems. Also, if you are interested with this work, we also prepare the audio samples and the source code. Of course, the source code pre-trained models also are available at this website. Okay, thank you.